Okay, Sulfur 16, the chemist still. Someone requested me to talk about back titration. First of all, what is meant by the term back titration? Back titration is the technique in volumetric analysis in which the amount of a given substance is not obtained by direct titration. In back titration, a given substance A, which is a standard solution that is in excess, is reacted with small amount of another substance B to give a product Q mixed with unreacted substance A. The unreacted substance A is then reacted with a standard solution of another substance C to give a product L. Equations to summarize the reactions above. Substance A standard solution, reacts with the substance B to give products as substance Q plus unreacted substance A. Unreacted substance A reacts with another standard solution C to give product L. Why is it called back titration? One of the reasons as to why this technique is referred to as back titration is because the calculations involves starting with the number of moles of the reactant used in the final stage of the experiment, followed by those of the reactants used in the initial stage of the experiment. This implies that during experimental procedure, we move from initial stage of the experiment to the final stage of the experiment. But during calculations, we move from the final stage of the experiment to the initial stage of the experiment. Steps followed in calculations of back titration. The steps will be explained basing on the previous summary of the reactions. The calculations in back titrations follow the following steps. Step 1. The number of moles of the standard solution of substance C are calculated basing on the volume of substance C used in the final stage of titration. Step 2. By use of the mole ratio of the reaction between C and unreacted A, the moles of unreacted A are calculated. Step 3. The total number of moles available in the total volume of the standard solution of substance A used initially is then calculated basing on the volume of the standard solution of substance A used initially. Step 4. The number of moles of substance A that reacted with substance B can be calculated by subtracting moles of unreacted A which reacted with C from the total number of moles in the total volume of the standard solution of A initially used to react with B. Sample question. You are provided with the following. Fa1, which is 0.6 molar hydrochloric acid. Fa2, which is 0.08 molar sodium hydroxide. Solid P, which is impure barium carbonate. You are required to determine the percentage purity of barium carbonate sample used. Procedure. Weigh accurately 2.5 grams of P into a clean beaker. Using a measuring cylinder, add 50 cubic centimeters or 50 mils of water and stir to form a paste, followed by 100 cubic centimeters or 100 mils of Fa1 and continue to stir until effervescence stops. Transfer the resultant solution into a 250 ml volumetric flask and make up to the mark with distilled water. Label the resultant solution Fa3. Pipette 25 mils of Fa2 into a clean conical flask. Add 2 to 3 drops of phenolphthalein indicator and titrate with Fa3 from the bullet until the end point is reached. Repeat the titration until you obtain the consistent results. Record your results in the table below. So after the process of measuring and titration, we obtain this. The mass of beaker plus P is 30.9. The mass of beaker is 28.4 and the mass of solid P is 2.5. The capacity of the pipette is 25.0. The final bullet reading in cubic centimeters. the initial burette reading in cubic centimeters, the volume of Fa3 used in cubic centimeters. Okay, let us determine the average volume of Fa3 used. The average volume of Fa3 is equal to 13.40 plus 13.40 over 2, and this gives 13.40 cubic centimeters of Fa3. Now, initially, barium carbonate reacts with excess hydrochloric acid to form products as shown, but the products are accompanied with unreacted hydrochloric acid. The unreacted hydrochloric acid is now in Fa3, which reacted with sodium hydroxide in Fa2 to form the products as shown in the final stage. But during calculations, we are going to start with determination of number of moles of sodium hydroxide, which is the second standard solution, followed by number of moles of unreacted hydrochloric acid, followed by the number of moles of hydrochloric acid that reacted with barium carbonate, and finally we can determine the number of moles of barium carbonate that reacted with hydrochloric acid. Thus we can determine the mass of pure barium carbonate that reacted and the percentage purity of barium carbonate. Okay, let us start by calculating the number of moles of sodium hydroxide in Fa2 that reacted with hydrochloric acid in Fa3. 1,000 cubic centimeters of sodium hydroxide in Fa2 contains 0.08 moles. What about the 25 cubic centimeters of sodium hydroxide in Fa2 will contain 0.08 times 25 over 1,000. These are moles, giving 0.002 moles of sodium hydroxide that reacted. Let us determine the number of moles of hydrochloric acid in Fa3 that reacted with sodium hydroxide in Fa2. The reaction between sodium hydroxide and hydrochloric acid can be described by the equation. From the equation, the mole ratio of sodium hydroxide to hydrochloric acid is 1:1. Or, from the equation, 1 mole of sodium hydroxide reacted with 1 mole of hydrochloric acid. What about the 0.02 moles of sodium hydroxide will react with 1 times 0.02 over 1. These are moles, giving 0.02 moles of hydrochloric acid that reacted. Let us determine the moles of excess hydrochloric acid in 250 cubic centimeters of Fa3. 13.40 cubic centimeters of hydrochloric acid contains 0.02 moles. What about the 250 cubic centimeters of HCl will contain? That is 0.02 times 250 over 13.4. These are moles, giving 0.0373 moles of excess hydrochloric acid. Next, we are to determine the number of moles of hydrochloric acid that reacted with barium carbonate in P initially. Okay, 1,000 cubic centimeters of hydrochloric acid in Fa1 contains 0.6 moles. What about the 100 cubic centimeters of hydrochloric acid in Fa1 will contain 0.6 times 100 over 1,000. These are moles, giving 0.06 moles of hydrochloric acid. Therefore, the number of moles of hydrochloric acid that reacted with P, remember P contains barium carbonate, is equal to 0.06 minus 0.0373 moles. giving 0.0227 moles of hydrochloric acid that reacted with barium carbonate in P. We can now determine the moles of pure barium carbonate that reacted with hydrochloric acid in Fa1. The reaction between barium carbonate and hydrochloric acid can be described by the equation. From the equation, 2 moles of hydrochloric acid reacted with 1 mole of barium carbonate. What about the 0.0227 moles of hydrochloric acid will react with? That is 1 times 0.0227 over 2. These are moles, giving 0.01135 moles of barium carbonate in P that reacted with hydrochloric acid. We can now determine the mass of pure barium carbonate that reacted with hydrochloric acid. The molar mass of barium carbonate is 137 times 1 plus 12 times 1 plus 16 times 3, giving a total of 197 grams. Therefore, 1 mole of barium carbonate in P weighs 197 grams. What about the 0.01135 moles of barium carbonate will weigh 197 times 0.01135 over 1, giving 2.23595 grams of barium carbonate. We can now calculate the percentage purity of barium carbonate. Percentage purity equals to the mass of the carbonate reacted over the mass of the carbonate measured times 100, giving 89.438%. Thank you for watching this video. This is Sulfur 16, the chemist. We meet.